Today I want to talk about one maybe important research line that is mainly overlooked. So it would be about trade-off-aware multi-objective optimization. So the main the main motivation for this type of studies would be in every network and in every generation of wireless communication systems, you always want to improve multiple key performance indicators simultaneously. For instance, we want to improve spectral efficiency, energy efficiency, latency, reliability, sensing metrics, and so on. In particular, for IMT 2030, you can see, for instance, this figure, which gives you an idea of how, for instance, for the spectral efficiency, it should be improved in our order of 5 times, for energy efficiency, even up to order of 100 times. But what the main issue is that whenever you want to improve one in performance metric, for instance, spectral efficiency, then the other performance metrics would be usually degraded. So for instance, if you want to improve latency, then you cannot wait so long for having larger packets, then the rate would be reduced. Also, you have to mainly transmit at higher powers. So it also would have an impact on energy efficiency. Also, it could affect reliability. It would be even more difficult to somehow improve all of these metrics together in multi-user systems whenever you have high interference. In this study, in this presentation, I provide 2 use cases for including RIS, and one including different techniques for next generation of multiple access schemes. But before that, we would have, I would present you one framework to tackle this type of difficult problems that you want to simultaneously consider different objective functions. So before we proceed, I would have a very short introduction to multi-user MIMO finite block length. So the rate expression that you can see on the top of this slide is actually the well-known normal approximation obtained by Polyansky and his co-authors. So, but the main difference here is that whenever we want to consider multi-user MIMO, you can have also multiple data streams per users. So you have actually a set of parallel channels. In the literature, there wasn't any closed form expression for the case you consider a multi-user MIMO, and we tackled this issue in reference number 3. So here, S would be the matrix, the covariance matrix of the signal we want to decode, and D would be the covariance matrix of noise, interference plus noise. And as you can see, whenever you have a shorter code word length, then the rate would be reduced. So meaning that whenever we want to have a lower latency, then we cannot wait so long to have enough packets to have a large code word length, which reduces the firstly spectral efficiency, and then through this metrics that you can see, it also reduces energy efficiency. What is important here, most of these metrics, or almost all of these metrics, would be a function of SINR, which is a fractional function. And for the delay or energy efficiency metrics, it would be also a fractional function of the rate. And you can see also one typical optimization problem considering jointly, for instance, spectral efficiency and energy efficiency. And here, beta is a weight to prioritize spectral or energy efficiency. So what you can see here, we would have usually a complicated problem. Then you have multiple constraints. Most of these constraints are not convex, so the problem would not be a convex problem. And mainly since you deal with fractional functions, and in case of MIMO or having, for instance, RIS, you have to optimize matrices, so it would fall into a fractional matrix programming. So here I want to firstly provide you a framework that we have developed for fractional matrix programming, specialized for multi-user MIMO with finite block-length coding. So firstly, I want to know if you are familiar with fractional programming or you have worked with in your research. If you ever worked with, please raise your hand to see. So just just a few. I hope you find it also useful. I mean, for the others, what we propose in the reference number 7 is actually two different solvers for both maximization and minimization problems. So whenever you have a complicated fractional programming that would, for instance, for the objective function, you have a summation of multiple ratio functions, and also you have some some constraints, then it would be a very difficult problem. So it is firstly non-convex, but in this reference, we propose a framework that can handle these difficult problems. So the main idea would be we transform this complicated problem into a preferably, and in most cases, a convex one. So it would be, you just need to find these surrogate functions using the hint here, and also maybe some additional equations from the paper. So I don't want to bore you with advanced mathematical equations. So in the next slide, I give you an idea of how it works. It starts with an initial point. So this is a simple illustrative case for the scalar case that you only optimize over x. And the function that you have is also, it's not a constraint optimization problem. So you start with an initial point, you transform the complicated problem, a fractional programming problem, into a convex one using the surrogate functions that are given in the paper. Then you easily solve this complicated problem, find a new point, for instance, x1. You repeat this procedure until you get a convergence. So examples of these problems in our field would be, for instance, a spectral energy efficiency trade-off, or maximizing energy efficiency, either sum energy efficiency, global energy efficiency, or maximum energy efficiency. So, but we also sometimes deal with minimization problems, especially whenever you deal with latency. You want to minimize the delay, which can be composed due to, for instance, if you have a multi-hop communication, or if you want to consider a point-to-point delay. So you have different delay expressions. So we have also considered the minimization case, and the idea would be simple or close to what we had already observed. So we have this complicated problem, we transform it into a simpler one, which is convex, and then we iterate until we get a convergence. So as I mentioned, the examples would be latency minimization and also mean square error minimization. So now I want to compare it with one of the well-known benchmarks in the literature, which is the Dinkelbach-based algorithm. So In the Dinkelbach-based algorithm, firstly, you can only solve a simple fractional programming problem. So it would be max-min ratio or min-max ratio fractional functions, but you cannot solve a more advanced one, for instance, sum of fractional functions or product of them, which would be maybe more interesting, especially for multi-objective optimization problems. So one main difference between our framework and Dinkelbach-based algorithms, apart from the wide range of optimization problems that we can solve, is that our solution is a single loop solution. So you don't need, for the Dinkelbach, it would be more difficult to implement it, since you have to implement it in a twin loop. And also, if you look at the convergence behavior, since it has a twin loop Dinkelbach-based algorithms, so you can see the convergence is not as smooth. It would be like having steps. So the main improvements would be achieved whenever you optimize the outer loop, but for the inner loop, the improvements would be marginal. So because of that, also the convergence behavior and implementation of our framework would be much simpler than these Dinkelbach-based algorithms. Now we go to, before we go to the examples, I give you a very short introduction. So we all know about RIS, and there were also a few nice talks for, RIS. So it would be maybe for this case that I consider would be just a bit simpler than the scenario that of the previous presentation. So it was this illustrative example would be for only a reflective RIS operating as a relay. Of course, we can also apply it to other more advanced cases similar to SIEM. So I think you all are familiar with the channel model for the RIS-aided systems. And one important point that I wanted to make here would be for the traditional or conventional RIS, we have a diagonal scattering matrix. But if we add more complexity to this, we can also realize a non-diagonal scattering matrix, which would be called the beyond diagonal RIS. So what is important here, if we look at, for instance, a single objective optimizations, adding complexity would improve the performance. But if we want to consider more, maybe more trade-offs in the system, if you add more complexity, make the scattering matrix, for instance, non-diagonal, you have to have also a circuit design. Then the number of circuit elements would matter. If you have, for instance, a fully connected case, then the number of circuit elements grows with the square of the dimension of the RIS. And because of that, one price that you may pay would be, for instance, a higher static power consumption. So now we can go to one illustrative example for the energy efficiency and also spectral efficiency trade-off of different RIS architectures. So for the figures that we have on the bottom, in the x-axis, we have a metric regarding spectral efficiency and another metric regarding energy efficiency. So as you can see, the more complexity you add, the better performance you get from a spectral efficiency point of view. But for the energy efficiency, it may not be that much clear. So depending on if your circuit design is somehow working well and you don't have that much static power per element, then it would be also great, and it can improve the energy efficiency as shown in this figure. But as the static power consumption of the circuit elements increase, then the energy efficiency would be lower and lower. So in this example, you can see that adding complexity may not necessarily improve all the different performance metrics simultaneously. One other illustrative example is about next generation of multiple access schemes. The focus in the presentation would be just on the cellular communications and particularly on the downlink. So maybe three important candidates for next generation could be rate splitting, NOMA, and SDMA. What is the difference between these three? So I give you just a very high level explanation. So the main difference would be in the way that you treat interference. In general, whenever you have a weak interference, the optimal way would be to treat it as noise. Whenever you have a strong interference, it's better to decode it and cancel it, or applying SIC. Then among these three methods, SDMA treats interference only as noise. So you may get an impression that the stronger the interference gets, then the worse performance SDMA would provide. But with RSMA, you have the ability to switch between these different strategies. So you can apply SIC, but if the interference level would be low, it automatically switches back to SDMA. So due to the time limit, I cannot go to the details. I just provide you another illustrative example for the energy efficiency and latency trade-off for the scenarios that you combine RIS with either RSMA or SDMA. One important point that you can see for all schemes is that whenever you want to focus on the latency or the delay, your system would operate in less and less energy efficient way. So the main reason is that to improve latency, you may have to transmit at a higher power. Then once the transmission power increases, then the energy efficiency would drop. So you can also see another difference in these two figures would be the power budget. If you increase the power budget, actually the energy efficiency would remain the same. The main reason is that, as I said, whenever you want to operate in an energy efficient mode, you may transmit at a lower power, which is in many cases lower than the power budget. But for the latency, the more transmission power you have, the better or the lower delay you will experience. So one other important thing that you can see, adding RIS to the system would improve the performance. But what is the game changing here would be RSMA. The reason is that in the scenario of these figures, we have more users than the number of transmit antennas at the base station. So the interference level is high. Then SDMA in combination with RIS cannot handle this interference. So one other figure that is also from this paper, it shows actually the impact of RIS and RSMA on each other. So whenever you have RSMA, so as the number of users grows, then you would have higher benefits achieved by RSMA. But what is more important, more interesting is the impact of RIS. So you can see a synergy here. So using RIS improves the RSMA benefits, but it's not always the case when the number of users is low, as you can see, equal to 2, which is the number of transmit antennas in the scenario of this figure. Then RIS would remove the benefits of RSMA. So this is also one other key point. So as a summary, I have presented one framework for fractional matrix programming. This can be applied to a wide range of optimization problems with multi-objective functions. What we have proposed is more general than the existing benchmarks and more specifically Dinkelbach-based algorithms. We had also a comparison between BDRIS and DRIS and showing that adding complexity would improve the spectral efficiency, but may not improve the energy efficiency. We had also reviewed quickly the performance of RSMA and in comparison, in combination with RIS. And as also future research, what we have proposed is general, but the examples that we had was for the case that we had a perfect CSI, and as also raised in the previous presentation. So it would be maybe not that much realistic for the RIS-aided scenarios. So robust designs would be an important research line. Other recent topics like movable antennas. Also, the framework that we proposed is suitable for integrated sensing and communications, but we have not studied it yet. Scenarios with mobile edge computing would also be applicable, would be solvable with the framework that we proposed. Another research line could be maybe digital twin assisted, hyper reliable and low latency communication. So this would be maybe solvable by our framework as well. And as a last slide, I want to thank also my collaborators. This presentation was based on the papers that were co-authored by Edward, and I wanted to thank all of my co-authors here, and thank you very much for listening.
Well, thank you for your nice talk. Are there questions in the audience?
Thanks, Mohammad, for the interesting talk. So it's a powerful framework you have there. But your talk was titled towards trade-off-aware resource allocation. So you are doing a Pareto boundary, right? Which still asks of the system designer to somehow find the trade-off point. So have you ever thought about doing this in a trade-off-aware fashion that might be automated for the system? So how can you really meaningfully do this trade-off? How can you prioritize different metrics? Any thoughts on this?
So in their studies, we just provided the Pareto figure. So that is actually showing all the operational points, but the optimal way or optimal operational point, we didn't focus on that from, for instance, an application wise. So that could be a very interesting research line, or it could be also maybe need some collaborations with industry. So to see which operational point would be optimal. So especially for the case that you have, for instance, energy efficiency and latency, since it would be very important for ultra reliable and low latency communication applications. So maybe you don't have to operate in, you have to operate in an energy efficient mode, but you sacrifice the latency. So that we have not mentioned which operating point could be optimal. So we just provided an overview for all possible operating points.